मैं डॉक्टर संगीता शर्मा, एसोसिएट प्रोफेसर पीजी डिपार्टमेंट ऑफ केमिस्ट्री, गवर्नमेंट इंटर कॉलेज बीकानेर। आज हम एमएससी फाइनेंस फिजिकल स्पेशल की 9th ए पेपर में यूनिट 4 लिक्विड स्टेट में इंटरमॉलिक्यूलर फोर्सेस के बारे में पढ़ेंगे। The finite compressibility and the relatively high density which characterize liquid in general point to the existence of repulsive and attractive intermolecular forces. The same forces that are known in gaseous form of fluid may be imagined to play a role also in the liquid form, except for the necessarily more important role of the repulsive force because of short average distance. It is necessary first to assume that the mutual interaction energy U of a liquid collection of n molecules is independent of the intermolecular energy level. It is thus assumed that the interaction between neighboring molecules are not sufficiently strong to excite new vibrational or electronic levels or to influence the occupation of rotational levels. Although it is the intermolecular forces of attraction and repulsion which lend the liquid its property, it is preferable to discuss the mutual potential energy U of molecules. As figure shows for two molecules A and B, the potential energy mu A B are theta A, theta B, phi A, phi B is both distance r and orientation theta and phi dependent. This leads to ambiguities when the force between the molecules F is equal to minus delta mu upon delta r theta phi is discussed. Since it ignores the orientation, the instantaneous potential energy depends on this orientation, but the thermal portion averages this dependency out in such a way that only a dependence on the distance r between the molecules remains. However, a new dependence on temperature T is thereby introduced. Mu is average is equal to ABRT is equal to double integration U exponential minus U of KT d omega A d omega t double differentiation exponential minus U upon KT d omega A d omega b, where omega is equal to sin theta d phi and mu is the orientation average potential energy. A simple two-body interaction. This is of 4 types. First, the simplest two-body interaction exists between imaginary hard spheres. Hard spheres are defined by following potential energy functions. Mu Hs r is equal to infinite for r is less than sigma and is equal to 0 for r equal to or greater than sigma. These are characterized by infinitely strong repulsion when an attempt is made to bring the sphere close together, then a distance sigma. They show, however, no model for liquid. They serve only as a first approximation when the repulsive forces between molecules or their sizes need to be emphasized. Second, a model which is very simple but a fair approximation to the real potential is the square wave model. The potential energy functions have the form mu s w r is equal to infinite for r is less than sigma is equal to minus epsilon for sigma is less or equal to small r or less or equal to capital R sigma or is equal to 0 for r is greater than capital R sigma. This is a three-parameter model epsilon, sigma and r which retains hard sphere repulsive properties but allows the molecules to attract each other with a constant potential energy minus epsilon when near each other up to a distance of capital R times sigma. In this figure, R is equal to 3. Although the square wave potential can reproduce roughly the macroscopic properties of a liquid, no physical picture of a model with this behavior can be set up. A third model is a model which has been used successfully to represent the interaction in one class of liquid, that is ionic liquid or molten salt, in the Sutherland potential, where again the repulsive force are represented by the properties of hard sphere but the attractive force are related to Coulombic interaction between charge. Here mu s u is equal r is equal to infinitive for r is less than sigma and cr minus for r is greater or equal to sigma. Fourth is Lennard-Jones potential. It is also termed the LJ potential. 12-6 potential is a simple model that approximates the intermolecular potential energy between a pair of neutral atoms or molecules as metal or cyclic alkane. This interatomic potential energy from Max-Born treatise on lattice enthalpies and is mu Lj is equal to 4 epsilon sigma upon r raised to 12 minus sigma upon r raised to 6 is equal to epsilon rm upon r raised to 12, where epsilon is the depth of potential well, sigma is the finite distance at which the interparticle potential is 0, r is the distance between the particles and Rm is the distance at which the potential reaches its minimum value minus epsilon. The distance related as Rm is equal to 1 by 6 sigma, which is almost equal to 1.122 sigma. These parameters can be fitted to reproduce experimental data on lattice parameters. Dispersion forces and multipole interaction. Uncharged polar molecules attract one another only on account of quantum mechanical reason and not an account of interactions of classical type. The dispersion force, as pointed out first by London, may be traced back to the quantum mechanical zero-point vibrations of the molecules, that is instantaneous non-isotropic change charge distribution inside the molecules. Although the time average of the instantaneous dipole moment is zero at any given moment, such a dipole induces a corresponding dipole in a neighboring molecule, leading to a net attractive force between these instantaneous dipoles and induced dipoles. The interaction leading to the perturbance of the electronic motion in one molecule by another is related to the perturbance of this motion by light, as measured by the dependence of the refractive index on the frequency of the light. The light dispersion, hence the name dispersion force for this interaction. The potential energy for the interaction of two spherical molecules is mu a b r is equal to minus 3 by 2 alpha a alpha b h mu a mu b mu a plus mu b minus 1 r minus 6. When two molecules are identical, mu r is equal to minus 3 by 4 alpha square h mu r minus 6, where alpha is polarizability, mu is the characteristic frequency, and h mu is 0-point energy. Equation valid for spherical molecule and is in fact the leading term of an expanded series of even reciprocal power of r, although the coefficient of r minus 6, r minus 10 and so on are not well established theoretically. The energy h mu can be approximated by the ionization potential of the molecule, so that the dispersion force between molecules of a liquid can be well represented in terms of the independently measurable quantities alpha and I. Mu r is equal to minus c r minus 6 with c is equal to 3 by 4 alpha square I. Dispersion force are major contribution to the additive potential even for polar molecules. Unless the permanent dipole moment is very large, the dipole-dipole interaction is less than the dispersion interaction. All three interactions depend on the reciprocal fixed power of the intermolecular distance. The quadrupole moment may be represented by QA is equal to half ZA E L plus L minus L U, where U is the unit tensor. So quadrupole moment vanish for an isotropic spherical charge distribution. The interaction energies for more important of these multipole interactions. Both the angle dependent instantaneous values and orientation its independent average values for six type of interaction is given in this slide. These are charge-charge interaction, charge-dipole interaction, charge-quadrupole interaction, dipole-dipole interaction, charge-induced dipole interaction, and dipole-induced dipole interaction. Other kind of interaction. Above interactions are physical types. Chemical interactions are more specific but very short range and strongly orientation dependent. In such interactions, the internal energy levels of interacting molecules are no longer unaffected, and a permanent dissociation of electrons relative to their state in the separate molecules occur. Strong dipole interaction occur when very polar molecules become adjacent to each other. The potential energy became large compared to their thermal, that is average kinetic energy, provided that the orientation is favorable. The molecules may then find a mutual configuration as a distance r0 considerably shorter than their usual repulsion envelope. Further enhancing the interaction, the potential energy for two identical molecules is mu aligned dipole is equal to minus mu square r0 raised to reciprocal power of 3.